The main idea of Lab 4 was to show the energy principle through an oscillating spring with a mass stretched at the end of the spring from its original position. Here we use multiple derivations of different equations to find all the necessary information we need to encrypt in our coding. So to start off, we find the oscillation time is equal to the 2 pi squared times the square root of the mass divided by the spring stiffness to rearrange that equation to give the spring stiffness equation. We also know that through Dr. Greco's explanation through the video that the magnitude of the gravitational force is equal to the magnitude of the spring force, where the magnitude of the spring force is equal to K sub s, the stiffness, times S, which is equal to the magnitude of the L, the length of the spring, minus the original length of the spring. Now, when we go up here back, we can rearrange this equation to find the initial length of the spring, where the magnitude of the L hat vector minus mg divided by K sub s, because the magnitude of the spring force is equal to the magnitude of the gravitational force. Now, continuing on, we go to the energy principle that will be involved, where we find that the change in energy is equal to the kinetic energy of the spring plus ball system plus the potential change of the potential gravitational energy plus the potential spring energy, which is all equal to 0 because no work is being done in this equation. The kinetic energy of the system is modeled by 1/2 mv squared. The gravitational potential energy is equal to mgh, mass times gravity times the height, and the spring potential energy is equal to 1/2 K sub s, the stiffness, times the difference between the length and the normal length squared. And we also use Newton's second law in this equation, which has always been stated. The final velocity is equal to the initial velocity plus the net force divided by the mass times delta t. And the overall net force, incorporating all these equations, is the net force is equal to the spring force plus the force of gravitation, where we get the spring force is equal to negative K sub s times L hat. And finally, incorporating all of this, we get that the final position vector is equal to the initial position vector plus the average velocity times delta t. Now, when we analyze Dr. Greco's video through Tracker, we see that the mass oscillates back and forth in the x and the y position because the mass was stretched initially when Dr. Greco let go of it. We see that the mass oscillates 6 times in the y direction, while it oscillates 5 times in the x direction. We will discuss why this is later when we address the what does this mean question. Now, when we plug the initial values into our tracker data, we use the mass given to us by Dr. Greco's video, and we use the position vector given to us found by the initial equations by looking at our tracker video. We insert more equations and more values, like the gravitational constant, the stiffness of the spring given to us through Dr. Greco's video, the length also given to us through the video, and the L hat, and S values, which I found by explaining through my Word document that was previously on the screen. We use more equations, such as the kinetic energy equation, the gravitational potential energy equation, and the potential spring energy equation. And we also use a time step, t is less than 9.307, because that was how long the video was recorded for on Tracker. We insert the gravitational force, the spring force, the net force, the velocity of the ball through Newton's second law, and the position of the ball found by using the velocity of the ball previously from Newton's second law. We insert the L hat, and S values one more time, and we also insert the energy equations used to find delta E one more time. Now, when we run our coding, we see that the blue ball, the model data, is almost identical to that of the red data, which is what's given to us through our tracker. Now, these are not quite identically the same, and this can be due to a few reasons. One could be that I just misplaced the tracking data when I went through the video, or more likely is that the blue ball completely negates air resistance. Because their air resistance is left out of this equation, the red ball and the blue ball do not identically match up to each other. Now, what does this mean? Is the energy principle satisfied given from these equations? Yes, the energy is 0, as the potential and kinetic energy of the mass oscillate continuously because there's no work done. When we edit the code slightly, we can see this, as it will be shown as it pops up right now. Bam, magic. With a few edits in our coding, we can now see the delta K, which is modeled in blue, delta U sub S, which is modeled in red, delta U sub G, which is modeled in green, delta K, delta U sub S, and delta U sub G, which is equal to the change in energy, which is modeled as yellow. Now, when we run this code, we see that everything oscillates except for the overall change in energy, which is modeled in yellow. This makes sense. We want this to be 0 because the work done on the system, the change in energy, is equal to 0. The gravitational potential energy plus the spring energy, or change of potential spring energy, plus the kinetic energy equals 0. To conclude, we will address the question why the oscillation periods are different between the x and y values. X is 5 oscillation periods, while y has 6. This is because the y component has a constant gravitational force acting upon it. This creates unequal forces acting upon the x and y components. So, using the math, the oscillations time t is equal to 9.307 seconds, we find that the period for x equals 1.8614 seconds, while the period for y equals 1.5512 seconds.